So, I'm going to quickly review what we covered so far. So we started a new topic, which is decision tree learning. And we started with basic concept, first overview of classification, and then basic concept in decision tree learning, how we represent trees, and for example, what each node represents, what are the branches, and what are the stop conditions, and so on. And today I'm going to further explaining like each part in more detail. For example, how for example to select the best attribute. This is what we didn't cover yet, right? So we didn't yet cover how to select best attribute at each level. And then pruning decision tree, this will be the topic for the next week. Now, as I mentioned before, so before we started event decision tree, I explained classification as a two-step process, right? So the first step was learning. In this stage, you have your training data, and then you just want to build your model based on the trainings data. So basically, you want to build a classifier or model that learn from your data. And this model can be like any like classification rules, decision trees, neural network, and so on. So this is the learning stage or model construction. We call this process induction. And then we have the second step, which is actually using the model. So once you created your model, you want to apply it to new, for example, unseen data, right? For example, you can use it for prediction, or you can also use it for evaluating the model using your test set. So for example, you have a test set, and this has true labels, but they're hidden from the model, right? So even though there are some labels, they are hidden from the model, and you can compare the predictions with true model, with true labels, and then from there you can measure accuracy, right? It is the percentage of test examples that are correctly classified by the model, or for example, how much actually your predictions were correct. And then we had this picture to better explain this process. So this is the first step where you have the training data. Here, each row representing a person, a column is an attribute, and finally the last column here showing the class label, right? Which is the lone decision in this example. So your algorithm looks at this data, search for patterns. For example, what could be an example of a pattern here? For instance, high income often means risky, right? Or low income may mean, for example, high income may mean, for example, safe, or low income, for example, may mean risky, something like that. And based on like these patterns, the algorithm build the classifier or your model. And so the classifier can be written a set of rules. This is just an example. For example, if age is youth, then, for example, lone decision is risky, and some other rules. So this is, for example, in case that the output is set of rules. And then this was the first step, or the learning step, right? Where you build a model or classifier. Now, the second step, we want to apply this. We can apply this so on the test set for evaluation, which means you apply the model in the test data. And as you see, your test set already has class labels. It's not that you don't have the label, but they are hidden from the model. And then you check, for example, how many you use this. For example, this usage is mainly for evaluation. For example, to see the accuracy of your model in prediction, right? So, for example, to see how many predictions are correct by comparing your predictions with the true labels. Or you can just use it for real prediction on really truly unseen data that are not labeled. So you see, for example, this data here. We know that the name, for example, is John Henry. Age is, for example, middle-aged. Income is low, but we don't know the lone decision, which is the class label here. So we can also apply our model on this kind of data for prediction. And then we pass this data to the classifier, and the classifier output a decision for us. Like this decision here is yes. And as I mentioned before, this yes here means safe, right? So because our real class labels are safe, risky. So this means safe here. Now let me run iClicker. So I didn't do it in my previous class today, but I decided to do it here. So this is not for this class, sorry. Here, selected poll, multiple choice. Can you see the questions?
Oh, no, just the classification learning techniques. There's no question right now.
Oh, so this is the
Okay.
wrong slide, sorry.
Okay.
So let's end this. So 83% selected option B, which is the correct answer, and 17% chose option A. So first one is testing and prediction are identical because both apply the model to unseen data. So they look the same, they do the same operation, but their purpose is different, right? So here we use the testing for mainly for evaluation, which is option B. During testing, labels are hidden from the model, right? Um, and we use it for evaluation because we want to compare our prediction with the actual true labels. But in prediction, you can apply it on really new unseen data where you don't have any label. You really do not have. It's not about like making them hidden, but they're not. You don't have them. And prediction require label data to work correctly. That is also not correct. Accuracy is computed using the training set, which is not correct too. None of you selected these options. And then here are just some of the classification learning techniques. So as I mentioned, I'm going to cover some of this during this course, such as, for example, decision tree learning, decision rule learning, Bayesian, this one, neural network, and KNN. Neural network if we have time, but KNN for sure. And so we also see an example of a decision tree. So here's your training data with some different kind of input features. So your input features, for example, homeowner and marital status, these are nominal categorical features, and annual income is continuous, right? Because this is numeric. And your class label at the end, this is the last column here. So you want to use these condition attributes or input features, right, for prediction. Now you may start with any of like these features to build your tree, and today I'm going to explain how we choose the best feature as a root node, or for example what would be the next best attribute and what would be the next, and so on. But for now, as I mentioned before, at this point you only need to know that each yellow box here, all these rectangles representing your nodes, and those are your condition attribute or input features that you use for actually testing, right? So you want to test, for example, this feature, and then you want to test this feature, and so on. And so your branches here, so for example, considering homeowner as an input, what does the branches show? What does the branch represent? Hello. So what are these? These are the unique values, yep, distinct values for each attribute, right? So the possible outcome of the test. So for example, when you split based on homeowner, what are the possible outcome? It could be yes or no. Person is homeowner, yes or no. And then for marital status, they could be single, married, and divorced. And so here, because we did a binary split, that's why we have married in one branch and then single, divorce in the other branch. And then finally with income, we have the same thing. We have binary split, and then we have a threshold value, like for example 80K. So income less than 80K goes to this branch, greater than 80K to another branch. And what are the leaves here? What do leaves represent? So nodes are representing our features, input features, and branches are showing the outcome of the test or distinct values of each feature. Final decision exactly, or the values that we have for our class label, right? For example, here, the decision should be either no or yes, right? So these are class labels, which are shown in the leaves. And so this is the like overall structure. And then you can use it. So imagine this is, for example, one decision tree, one possible decision tree based on this training data, right? Now, when you build this tree that you see here and a test, for example, you want to now predict, for example, what is the defaulted borrower, for example, for this. You want to apply it on your test data and see, for example, if you have someone who is not homeowner and who is married and annual income is, for example, 80K, then what would be the class label, or what is the prediction here? So you always start from the root node, and then you go into branch based on, for example, the value possible outcome of each test. So homeowner is no, so we go to the right branch, and then here we check for marital status. It's married, so again we go to the right branch, right? And then here we reach to the leave. So we don't even need to check for the income at this point, right? Because all people who are not homeowner and whose marital status are married, they are all belong to class no. And this you can see here. So for all the cases, you have the homeowner no, right? And for example, no married here, the class label is no. Again, no married here, class label is no. No married, again, row 9, the class label is no. So because all examples belonging to this case belong to the same class label, we reach to the leaf, right? So there is no point in further splitting because all of them belong to class label no. And this is what we see here. Now, this is another decision tree based on the same data. So there could be more than one tree that fit the same data, right? And that's why we have to know which one is the best, right? So for example, which attribute to choose at first. Is this one better, or for example, this one, or many other possible ways to create the tree, right? So this is what I'm going to explain today. So this is another example. And so this whole process that, as I mentioned before, for the classification, which can also apply here, decision tree is also a type of classification. So induction is the process where you learn from your training data and you create your model. And then deduction is when you apply your model to the test set. Now, let's focus specifically now on decision tree learning. So what is the objective here? Objective in decision tree, we want to learn a decision tree, right? We want to learn a decision tree from our training data. And this training data, of course, has class labels, right? So we have like some known class labels. And once the tree is learned, when you learn your tree, then you can use it, you can apply it to your new unseen data, for example, to classify new examples, like the examples we've seen before. There are many algorithms here, so this slide is just showing some of the well-known decision tree learning, such as, for example, Han's algorithm, ID3, C45, and so on. So you don't need to memorize this. And then we also talked about this example. So this is an example of the training data. And each row here is representing a training example. So as you see, training examples or cases. So when I say case, I mean each row. So each row represents a case or a training example. Now, these are 14 days representing the weather information for 14 days. What are the condition attributes or your input features? So your condition attributes are just your input features that you use for testing and splitting your data. You want to use them for prediction, right? So they will help you with that. And then you have the class attribute, target attribute, or decision attribute, or simply our class labels here, which is in this example is play tennis, right? Can be yes or no. Now, so the decision tree is taking a data like this, right? And it uses these condition attributes and it try to predict the class attribute, which are these ones. Now let's see an example of a tree based on this training data here, right? And see the structure. So I already explained what each node or branch represent. So here we just do a review. So each internal node, right, testing one attribute. For example, we check on Outlook, then we check, for example, on humidity or wind, and so on. So we had several attributes, Outlook, humidity, wind, temperature, and so on. So these are the attributes that you will use. And then each branch, so for example, let's say your attribute is Outlook, right? So you want to test an attribute that is testing Outlook. If Outlook is sunny, then you do something. If Outlook is overcast, then some other things. And if Outlook is rainy, also another branch. So each branch is representing a distinct value of each attribute, which is also showing the test outcome, right? And so sometimes, for example, here in this example, Outlook when Outlook is overcast, so if you look at the data, in all examples where Outlook is overcast, so if you see here, like this day, and these 2 days, what is the class label here?
Yes.
All of them belong to class yes. So do we need to further split the tree from this branch?
No.
No, we don't need, right? So we don't need to further split from here because all cases belong to the same class label. So when I'm saying one stop condition in decision tree is when, for example, all cases belong to the same class label, this is what I mean, right? All cases in that branch now belong to this, like the same class label. And that's why the branch overcast, you don't split further there. So you see it here. So you just reach to the leaf. So this is one stop condition, or this is when you reach to the leaf node. How about when Outlook is sunny? So let's go back here. When Outlook is sunny, for day 1 and 2, play tennis is no. So class label is no. We also have day 8 and 9, which are sunny, but we have mixed class labels here, right? One of them is no on day 8, and day 9 is yes. Again, day 11 is yes. So we have mixed results. And so far, we had 3 no and 2 yes. So out of 5 days that are sunny, 3 of them belong to the class no, 2 of them belong to class yes. So do we need to further split the tree? Yes, we have to, right? Because we don't know what is the answer. Should you write yes or no? We don't know. It depends. It depends on some other features. So now let's choose another attribute. So at this point, you don't need to know why I put humidity here, for example, right? I'm going to explain it later today. Now let's say humidity. So after checking Outlook, sunny, humidity, let's say, is the best attribute to move forward. And then it means if Outlook is sunny, so only we are now working on that subset of the data, not all 14 days, but only those 5 days that the Outlook is sunny, right? Now, in those 5 days, if humidity is high, what would be the result? And let's see if we reach to the leaf node, which is the case here, or for example, we have to further split. So when Outlook is sunny, as you see here, when Outlook is sunny, which is this row, right? And this row, and then also this one, and this one, right? For these 5 rows, when Outlook is sunny and humidity is high, right? So humidity also should be high, here is also high, and these 2 are normal. So we only are considering like these 3 rows, right? So day 1, day 2, and day 8. So for these 3, they all belong to the same class label, right? They all belong to class label no. Therefore, we know that we reach to the root. So here we started from Outlook, right? And we said here is sunny, here is overcast, here is rainy. And then for sunny, we said, okay, for overcast, it was clear. All classes belong to, for example, the same class label are cases. It was yes, so we reached to the leaf and we stopped here. For Outlook sunny, we had 5 instances, but there were mixed labels, so we had to test in another attribute, which was, for example, humidity. And now for Outlook, for example, humidity has also 2 possible outcomes. Could be high, right? Humidity could be high or could be normal. Now, if Outlook is sunny and humidity is high, then we reach to the leaf again. So this is again another stopping condition, because now we reach to the point where all examples here, all cases belong to the same class no. What about here? So if Outlook is sunny and humidity is normal, so Outlook sunny and humidity normal, so like this one and this one, right? So they also belong to the same class, right? And so here is yes, and so this is also yes. So we reach to the leaf node again. And this is the way that you continue building your tree. And there are several, like 3 stopping conditions. One of the main stopping conditions is when you reach to the point where all cases belong to the same class label, which we have seen so far. But there are also other stopping conditions. For example, you may reach to the point where you are you don't have any feature to split on anymore, right? And so if that was the case, then you, for example, if there is no more attribute to split, but still you have, for example, mixed class labels, then you use a majority, for example, class. That is for example, if 3 of them are yes and 2 are no, then you use yes. And then another like last condition for stopping growing your tree is if, for example, you don't have any data point to continue anymore. That's also another option. So so this is how classification works, right? So you start at the root and you test the attribute at that node, and you follow the branch that matches the example, and you repeat this until you reach the leaf. So the label at the leaf is your prediction. That could be yes or no in this example. So for example, if outlook is sunny, humidity is high, right? And wind is strong. So what would be the prediction? So outlook is sunny, humidity is high, so you don't even need the wind value anymore. So this is no. And so this is also an example here. Let's see this example, another example. So here's another training data set. And here, this is following example from Quinlan ID3 example. You don't need to know like this, just this is just for your information. And so we use a top-down greedy approach. What do I mean by that? So by top-down, I mean that we start building our tree from the top, which I did so far. And by greedy, I mean just non-backtracking. So at each iteration, you just select the best feature at that moment to create a node. So we are using like divide and conquer way method. So I'm going to explain more about this today. But for now, let's see this data. Each row here is one customer, data about one customer. Now in each column, you see different features, right? For example, what are the condition attributes here?
Income, students,
Age,
credit.
income, student, credit rating, also age, right? So these are your condition or input features. So these are your attributes. Sorry, this is not the best. And this is condition attributes. Now, what is your class label or output variable? This is your class label, right? Which can take yes or no. Now, so again, you see the same structure, right? So your condition attribute on the left and your class attribute on the right. And the decision tree learning method, this doesn't care about like the meaning of like the attribute. We just look for patterns. And so here, if you want to build a tree based on this, let's say, so I haven't explained how to choose the best feature as the root node. So let's say I say best one is age. Okay, so let's choose from the first one. What type of attribute is age? Is it nominal, ordinal, categorical?
Would it be nominal?
Nominal, categorical. Why?
For age, nominal because there's not exactly an order.
But is it a continuous, or is it a numeric continuous, or is it discrete? Is it categorical or not?
It's categorical.
Age is categorical. So here it is converted to categorical, right? So in this case, that is correct. If we had age like, for example, 23, 30, 54, 60, and so on, then in this case, age would have been numeric continuous attribute, right? But right now, what we see here is a categorical feature, right? So we converted it to categories like less than, for example, 30, so 30 to 40, so three categories, right? And greater than 40. Now, so let's say age, so based on, for example, this, how many branches I can have here? What are the branches? I'm building the tree here. So we are building the tree. What are the branches here?
Is it for bias computer or age?
For age. For
Okay,
by
then
computer, so by computer is just our class label, right?
yeah.
So we
it's-
don't have it in our tree.
Yeah. Okay, so the age would be 3 branches. Oh,
Yeah,
somewhere. Yeah.
that's correct.
So less than equal to 30, 30 to 40, and then greater than 40.
Exactly. So we have like these three, right? And then greater than 40. Now we want to see if we have to continue or we have to stop. So for example, age less than, or for example, less than 30, right? For this one. What is the class label? So let's see. So we have it here, here. So far class labels are no. We have it again here, but class labels are mixed, right? So we didn't reach to the root node. We should not stop. And since we reached to the, since we have mixed class labels, right, as you see, 3 of them belong to class no, 2 of them belong to class yes, so we need to further split and finding another feature. Now this could be any of these features based on the calculations that I'm going to explain later today. So this could be income, student, credit rating, or anything. Also, let's say this is income, right? And then based on this, again, we continue splitting. Same here, for example, for age 30 to 40. So for example, for age 30 to 40, which is here, class label is yes. Again, sorry, this is a typo. So this should be, because this is less than or equal to 30. So this should be 31. Okay, so this, you can consider it as a typo here. This is yes, and these are also yes. So should I split here?
No.
No, we reached to the node, right? We reached to the leaf node, sorry. Yes. And then finally, the same procedure for example, this branch, right? So we continue the same for greater than, age greater than 40. So again, we see the mixed labels. And because of the mixed labels, it means that we have to split on another feature. So we are going to learn how to choose these features. For example, this could be another feature, whether it's a student or not, or credit rating or anything. And then we continue in all like these branches again the same way, right? Until we, like at each branch, we reach to the leaf. So we continue until that time, which means all classes belong to the same class label, right? All cases belong to the same class label. And so this is for now. Do you have any questions except for like how to choosing the best attribute, which I didn't teach yet? Do you have any questions? And so here you can see sample decision tree learned from the previous dataset that I just showed you. So at the root we have age. Why do we have age here? We don't know yet, because the algorithm decided this was the best split. I'm going to explain it later today. If age is between 30 to 40, as I explained, the outcome is yes, right? The prediction is yes. So no further tests are needed, because all classes belonging to this case, sorry, all cases in this branch, where, for example, people between 30 to 40 years old, they all belong to class yes. But for the other ones, for example, here we chose a student, because, for example, for the age less than 30, we had mixed results. So some of them belong to class yes, some of them no. So we had to further split on another attribute. We chose student. Again, it's a question mark because I haven't explained it yet. But I'm going to explain later today. And then we continue splitting. So until now, what I would like you to know is that what is classification, and that decision trees type of classification method, and that we, for example, what is induction, deduction, and classification as a two-step process, the representation of, for example, your data in terms of, for example, decision tree, how you build a decision tree, except for choosing the attribute. When, for example, we should stop growing our tree, right? For example, when all the cases belong to the same class label, and that is your stopping condition, and so on. So this tree is actually showing uh, an important idea, and that's it. That's different path are testing different attributes, right? So for example, this path is testing, for example, a student. The other path is, for example, testing credit rating. So you do not, it's not that not all attributes are used everywhere, right? And once we reach a leaf, it means that you reach to your final decision. So it means that, for example, at this point, all cases belong to the same. For example, class label, here the same thing, here the same thing, here the same thing, and here the same thing. And that's why we stopped. So the second question, so everyone should answer correctly. So we have 17 responses so far. So the correct answer, and most of you chose the correct answer, was option C, which is so the question asked in a decision tree for classification, which statement is true, right? So option C says branches correspond to outcome of attribute test, right? For example, if your node is Outlook, right? So branches coming out of Outlook are possible values of Outlook, right? Which are sunny, which are, for example, overcast and rainy. And as I said, each attribute is a test, right? So we are testing each attribute, and then branches are outcome of that test. And so this is the correct answer. So the first one says internal nodes represent class labels. Are they? Are internal nodes representing class labels? No, the leaves are leaves representing class labels. Because what is a class label? So this is your class label, right? So these are class labels. Which are your leaves? So yes, no, these are your class labels. This is your class label, right? But the attribute are your nodes, right? Age, student, credit rating. So these are your input features or condition attributes. And therefore, this is not correct, option A. Option B says leaf nodes represent attribute tests. So this is all I already explained. This is also not correct because leaf nodes represent class labels. And finally, every path from root to leaf must test all attributes. No, we do not test all attributes in each path. For example, in this path, on the left, on the far left, we are only testing age and student and not all attributes, right? And so now I'm going to continue on. So that's good. We still have 40 minutes, and I'm going to explain how we choose the best attribute. But before that, about building decision tree, normal procedure, as I explained before, is top down. So you start from the root and then you go downward in divide and conquer manner. By just recursive divide and conquer, I mean at the beginning you choose one attribute for the root node, right? For example, you choose Outlook, and then you create one branch. You create one branch for each possible value of that attribute. So, for example, when you choose, for example, Outlook here, right? So if this is representing Outlook, then we create one branch, for example, this branch, for each possible value of that attribute, for example, for being sunny. And then another branch for another possible value, which is, for example, overcast. And then another branch for example, rainy, right? And so we split the data like this, and each branch is getting only the examples that matches that branch, right? So for example, here we started with 14 rows, right? So we had day 1 until day 14, right? So this was the data. We had 14 rows in our data. Now, out of those 14 days, only 5 of them were sunny, right? So here, this branch is only getting those 5 examples, right? And from those 5, 3 of them, I think, belong to class negative, 2 of them positive, if I'm not mistaken, something like that. And then we had 4, for example, Outlook overcast, and 5 Outlook rainy. And you'll see like just in a few minutes why I'm explaining this. Now, let's see this. So when I'm talking about divide and conquer fashion, I mean that when you start from the root and going downward, so at the beginning you choose one attribute for your root node, then you create branches for each possible value as I explained, then you split and each branch getting the examples that match that branch. And then you repeat the same process, right? So you repeat this recursively for each branch. So I was explaining only one branch for Outlook Sunny, but you're actually doing the same process for each branch. And that's the recursive part, right? And when do you stop? When all examples belong to the same class, or when there are, for example, no attributes left, or for example, you don't have no more data. And so here is also the algorithm. So this is the pseudocode for the decision tree algorithm, and you don't have to be like, don't worry about memorizing these steps. You don't need to do that. Just focus on the logic. So we start by creating a node, then we check the data. If all examples belong to the same class, we stop. So and then if also, for example, there are no attributes left, so if attribute list is also empty, then this is also another stop condition. In that case, we label the node with the majority class, right? So return n as a leaf node labeled with the majority class. And if they all belong to the same class, so this is a leaf node. So this is what is explaining here and what I already explained several times. And otherwise, we can choose the best attributes, right? So if so, these were the stop conditions. If for example, all cases belong to the same class, you stop. If, for example, there is no more attribute, we stop. But otherwise, you have to continue splitting, right? So you have to continue. And then so you choose for choosing the best attribute. I'm going to explain how you do that. So that attribute becomes the test at the current node, and then you again continue splitting the data based on that new attribute, and then for each split you repeat the process, and this is where the recursion is happening. And so that's why we have like this for loop here, and eventually all branches end in leaf nodes, and the tree is complete. So you just have to know the logic. So let's see this process with this example here. So we take the training data and we choose an attribute for the current node. For example, here, let's say our root node is Outlook, right? So let's say here we have 14 days. And so possible outcome for the Outlook are sunny, overcast, rainy. Now, which days are sunny? D1, D2, D8, D9, D11. So these are the days where Outlook is sunny. Then the days where Outlook is overcast is D3, right? D7, D12, and D13, and the rest are rainy. And so each subset is handled separately. So for example, for overcast, because all examples, we've seen that all examples when the Outlook is overcast belong to the same class label, which was yes. So you have to stop there. And so in this case, sorry, I have to show that later. So in this case, you stop here. For the Outlook sunny, right? For the Outlook sunny, because you didn't reach the stop condition, you have to continue. For example, splitting on another attribute, let's say humidity. So for Outlook sunny and humidity, if humidity is high, then you reach to these 3 days. That is day 1, day 2, and day 8. So these 3 days, Outlook is sunny and humidity is high, and all of them belong to class no. That's why you see this negative or minus here, minus sign here, right? And if Outlook is sunny, humidity is normal, you see positive because they belong to class yes. This is how we represent it in our this is how we represent them in your trees. So please be mindful to do the same way in your exam, and also in your assignment. Assignment 1 will be decision tree, so I want you to follow the same process. And then for this branch again, we do the same. For Outlook rainy, we have these days, but not some of them. For example, D6 and D14 belong to the class no, and D6 to D14, sorry, D4, 5, and 10 belong to class yes. So because we have mixed results, we have to further split, right? So we split, and then for example, these two belong to class no, and these belong to class yes, because all cases belong to the same class. That's why we reach to the leaf, and we stop. Now, this is just summary of what I explained so far, and so except for the first question, that these are like the design issues in decision tree induction. So the main problems: how to select an attribute for a node, that I'm going to explain in a few minutes. when to declare a node terminal, that I explained, when all cases belong to the same class label or we don't have any more attribute, and how to assign a class to a leaf node, or how to label a leaf node. So one option is to use the most common class, and another one is just using the output class probabilities. Now I click here question 3. Give you 20 more seconds. 15 people responded so far.
Professor, I'm trying to select multiple answers, but it just allow only one.
Oh, okay. That doesn't matter. Because the questions are not marked, so I only mainly use them just for a review purpose, like for increasing the engagement and for participation. So it's fine. Sorry for that. And I think I've created other questions. I didn't know iClicker doesn't allow for multiple selection, or maybe I had to do specific setting. Okay, so the results, 83% chose option B, and 17% chose option A. So the correct answer is option A, B, and C. So let's see all options. So question asks which options are valid stopping conditions in building a decision tree. First option, all examples at the node belong to the same class. So when all examples belong to the same class, which we see that this means pure, so nothing is left to learn, right? So this is one valid stopping condition. The second one, there are no remaining attribute to split on, right? So if we don't have any more attribute to split, so then we have to stop. And C, no training example reaches the node. This is another one. So we label then, for example, using the parents majority class. But for example, the entropy of the node is high. Sorry, I didn't mention entropy yet here, but it measures impurity of a node, which is not relevant here. And the attribute with the highest information gain has many distinct values. Also, this also doesn't apply. So I'm glad most of you chose the correct answer. So I missed the first question because it was at the start of class. Will I still be marked as here? So you're not going to be marked as I'm using this as a poll and not quiz, so mainly for participation purposes. And so don't worry about whether you answered a specific question or not, or if your answer is not correct. Can we use the attribute more than once in the decision tree? So not usually. So it doesn't make sense, right? So when you split on an attribute, then you're already partitioning your data based on that attribute, right? So for example, if you select Outlook and you are splitting on Outlook, then it means, for example, you're partitioning your data for example, 3 subsets. One subset would be Outlook sunny, one subset Outlook overcast, and one subset Outlook rainy, right? So splitting it again, it doesn't add any useful information, right? So not in the same path, I would say. So you may still use it in different branches, but not in the same path. And so let's continue now. How to select the attributes? So at each node we must choose one attribute. Now looking at these 2 trees here, so both of them are starting with the same data. So in both examples, on the left, for example, you see 29 positive, 35 negative. That is 29 belong to class yes, 35 belong to class no. And same thing here, right? The only thing that I would like you to know at this point is that after splitting, even though like both of like these starting this with the same data, the distributions after splitting are different, and some splits create cleaner groups, like for example this one or this one, but some of them keep the data mixed, like for example this one. And so we want to see which attribute produces the best. We want to see which attribute produces the best result. And so to answer this, I have to explain some selection criteria. So you can see here. We are not going to cover everything in this course, but what I'm going to cover and are the most important ones are information gain, gain ratio, and Gini index. So these are going to be covered in this class. So let's see what information gain is. So the first measure for selecting the best attribute. So in general, we have to calculate information gain for all attributes, for all input features. So for example, let's say if your input features are outlook, are wind, temperature, and so on, and for example humidity, if you have like these 4 features, you have to calculate information gain for all 4 features, and whichever has the highest information gain is the best attribute to choose as your root node. Okay, so now what is an information gain? So the goal of information gain is to, for example, you want the result, you want to split it in a way that your resulting subsets be as pure as possible. And by pure, I mean mostly one class, and ideally only all cases belonging to one class. So this is an ideal split, right? Because 29 out of 29 cases belonging to class yes, and 35 belonging to class no, based on, for example, this feature, this attribute, let's say this is A, attribute A, or anything, outlook, temperature, anything. So an ideal split would be this 20, for example, this split would be 29 yes, 0 negative, and then this one is 0 belonging to class yes, and 35 belong to class no, right? So this is what you want, and this is an ideal split. But like in practice, this is not that ideal, because it also causes overfitting, especially if you come up like with very like lots of like distinct values. I'm going to explain more about this now. So for now, just I would like you to know that the goal of information gain is to make an split as close as to an ideal split, which is like make it as pure as possible. And so information gain is measuring how close we are to this ideal split. So when you calculate, for example, information gain for several features, for example, for age, for income, for example, other features, then any of like these attributes that has the highest information gain, that is the attribute that you have to choose at each level. Another important thing is that information gain is based on a concept called entropy. So before I can explain the formula for information gain, you need to know what entropy is. So entropy is a measure commonly used in information theory that characterizes impurity of an arbitrary collection of examples. So what do I mean? In simple words, entropy measures impurity or uncertainty or chaos or disorder, or you can think of it as a confusion. Okay, so if all examples belong to the same class, can you tell me whether entropy is high or low? If all examples belong to the same class, yes, entropy is low. Entropy is 0 if they all belong to the same class, because there is no confusion, right? There is no impurity. As I said, entropy is a measure of impurity. So if all examples belong to the same class, means the data is the purest. And if this is the purest, means the impurity is 0, means entropy is 0. And so entropy is just telling us how mixed, for example, your data is at each node. So we say, for example, a node is pure if all examples belong to the same class, which in which case entropy is 0. Of course, the purer it is, the lower the entropy, and the most impurities, the higher the entropy. And as your classes become more mixed, entropy increases. So here is the formal definition. So we start with a set S of examples. Suppose we have K classes. So entropy is just measured using the class probabilities, as you see here. So for each class, we compute its probability in S, and we combine them using this formula. So let me also write. What do you mean by it's not chaos, it's orderly?
About the previous slide where you were saying if everything belongs to the same class, is entropy 0. That's what I was trying to answer.
Yeah, thank you. Yeah, exactly. And now I'm going to explain better with this formula here. Now, you don't need to memorize this because I'll allow you to bring cheat sheet on your exam day, which should be limited to just one single page. But I'm pretty sure like after just a few examples, you will memorize this, because even if you do it for just one decision tree, since you have to calculate entropy and information gain for each single feature or each single attribute, then you will memorize it in any way. But you don't need that. So entropy is minus sigma I 1 to k, probability of Ci, so these are our class probabilities, multiplied by log of PCI, where PCI is the probability of examples in S that belong to Ci. So, as I said, entropy is measured using the class probabilities. For each class, you compute this probability in S, and then we combine them using this formula. And you don't need to memorize this formula. If all examples belong to one class, entropy is 0. So if all examples belong to the same class, that is S is the purest, entropy is 0, and we already mentioned that. So mathematically, if you want to see why this is happening, is because, so let's say we have two classes, okay? So let's say we have two classes, and so K is 2, right? And your classes are, let's say, yes and no, right? C1, C2. So you have only like C1, C2. One for example, yes, one for no. So these are your classes. And so you want to, and we know that all cases belong, for example, to class yes or C1. So what is the probability of C1 and what is the probability of C2 if I say all cases belong to class C1? What is this?
Yeah. Would I know the entropy, would the probability be
yeah, just the probability.
Will it be 100?
Exactly. So this is 1. And then the probability of class 2 is 0, right? Because no case belongs to this class, so there is no chance for this, no probability, right? So this is 1 and this is 0. Now put it in this formula. What will be the entropy? So the entropy will be -1, right? Multiplied by log of 1, right? Minus 0 multiplied by log of 0, right? Which is, so what is this? What is log of 1? When we say log of 1, right? So it means 2 to the power of what is equal to 1. So this should be 0, right? Any number to the power of 0 will be 1, right? So this is 0. So -1 multiplied by 0 is also 0. And then here is 0 multiplied by log of 0. So this is also 0. And so 0, 0 gives you 0, right? And so that's why entropy of S is 0. And similarly, here, if half of the examples in S belong to class 1 and the other half belong to class 2, entropy is 1. The same way, because if you write it, it will be -1 multiplied by, so let's remove these just to avoid confusion. And here, so I want to calculate PC1 and 2 from the beginning. Now again, this time I say we have half of the examples belong to class C1, half belong to class C2. So each of them is 50%, right? Or 1/2, right? So in the formula, the entropy of S, when half of cases belong to class 1, half belong to class 2, it will be -1/2, right? This is the probability of C1, multiplied by log of this, right? And then what is the log of? It means 2 to the power of what is that number, right? So the same thing here. So log of this, and so 2 to the power of what will be this? -1, right? This is minus 2 to the power of minus 1, right? This is equal to 1 to 2 to the power of 1, right? So this will be minus 1, so this will be minus 1, right? And same thing here. And so the result will be 1, 2 plus 1, 2, which is 1. So this is the highest impurity or highest entropy. And this is because this is the maximum confusion, right? Half of them belong to one class, half belong to the other class. So the ideal case, as I said, is when most, like all classes belong to one class, or like at least like most classes belong to the same class. But as you like get far from here, that means, for example, half belongs to one class, half belongs to the other class, it means it is highly impure, right? So the entropy is highest. Now you can calculate the same way for any case. For example, 9 examples are in class 1, 5 examples in class 2, right? So it's when 9 class, so we have 14 cases in total, right? 9 out of 14 belongs to class 1, so probability of class 1 is 9 over 14, multiplied by log of that, and then here we have 5 over 14, which is probability of class 2, right? And then you can calculate this using your calculator. And of course, in your exam, you're allowed to bring your calculator. And please make sure that you're comfortable working with a calculator that you're bringing to your exam session. So this is based on the experience I have from last year. Several students had a really hard time working with their calculator. Some of them forgot to bring a calculator, so they had to borrow other students' calculator, and they didn't know how to work with that. And so you have to make sure that you can make all these calculations using your personal calculator. Is that clear?
Yes, Professor.
Okay, great. Then so far we assumed we can just split on an attribute, and how we split depends on the attribute type. So there are 3 main types: nominal, ordinal, which are for categorical attributes, and then continuous attributes. And we also need to decide how many branches we allow. So sometimes we split into 2 parts, that's binary split. Sometimes we do it like in more than 2 parts or more than 2 branches, that's a multi-way split. So for example, these are the examples. This is an example of a multi-way split. Marital status can be single, divorced, married. So you just create one branch for each distinct value in that attribute. Or another way is just a binary split. Even if you don't have like 2 distinct values, even if you have multiple distinct values, you may still do binary split. Like this, for example, married, not married, which means single, divorced. Or single, not single, which means married, divorced, and so on. Now this is for nominal attributes. Now, what if we have ordinal attributes? In the case of multi-way split, it's the same. For example, let's say you have an ordinal attribute like shirt size. Shirt size is ordinal because it has order: small, medium, large, X large, right? And so you can still use a multi-way split, 1 branch for each size, and that's okay. And you can also use a binary split. So now here, the only difference with the nominal one is that you have to take care of the order. So you have to make sure to preserve order in your split. For example, this one on the left is allowed because you have small, medium here in one branch, and in another branch you have large, extra large, and the order is preserved. The second one, is this allowed? A small in one branch and then medium, large, extra large.
Yes.
Yes, this is also allowed. What about this split? The last one?
No.
No, it's not, right? Because it doesn't preserve the order and breaks the meaning of the attribute. And so this is not allowed. Now, for continuous attributes, again, you have both options. Binary split, so you choose a threshold, for example, income greater than 80K. And then if it's greater than 80K, for example, yes. If not, no, and so on. So this is your threshold, 80K. And then you can also do a multi-way split. So you can divide your income into intervals. For example, less than 10K goes to one branch, 10K to 25 into another branch, and so on. So this is also another way. And so focusing on continuous attributes here, so these are numeric values, like for example income or age or any numeric attribute. So there are two main ways to handle them. One is discretization. We talked about discretization a lot in data preprocessing. What was it? What was discretization? What is it? Discretization?
Splitting. How do I say this? Like basically reducing the number of values into specific.
So think of discretization as a data transformation technique. So as a data transformation, if you recall, we could convert the continuous attribute into some categories, right? For example, you have income values, right? You have several income values. You can make it, for example, instead of distinct values, like for example, 50K. So instead of having 50K and then 55K and so on, and then 100, 150 and so on. So instead of having like all these distinct values, detailed values for the income, you can just basically have, like for example, convert it to categorical, like for example, either different intervals, like for example 50 to 100, 100 to 150 and so on, or simply you can just have them like low income, medium income, or high income, right? So these categories now, like if you convert it like this, low, medium, high, then this is ordered now. And so the attribute become ordinal. And so the ranges can be created in different ways. As I said, you can do equal with. So these are just the same term as I explained before. So like equal interval bucketing, equal frequency bucketing. So it just means like equal width intervals, equal frequency, and so on. And so you can do discretization once at the beginning, which means it's a static. That's a static discretization, or just do it repeatedly at different nodes. That's dynamic discretization. Or the second method, so that was the first method. The second approach is just binary decision. So binary decision, you choose a threshold value, for example, for age, or even for income, right? Or age, doesn't matter. For example, age less than, I don't know, 40 years old, right? So for age less than, for example, 40, or age greater than or equal to 40. For income less than 50K, or income greater than or equal to 100K, right? So that's your threshold value. And then your algorithm tries as many like threshold as is possible to just selecting like the best one. And this is most expensive because then you have to choose several thresholds, but it's also more accurate. And so these are just providing some information about like dealing with different types of attributes. So now let's look at this example. Before splitting, we have 20 records, right? 10 records belong to class 0. So the first 10 records belong to class 0. And the last 10 rows belong to class C1. So they, like the data here is perfectly mixed. Now we want to considering different test conditions here. So how many test conditions can we have?
3.
Right? So we have customer ID, gender, car type, shirt size, like all of this. And then you have your class label here. So these are your condition attributes. So I intentionally put customer ID here because I want to explain something based on this. Now, so let's say you want to test based on gender, car type, and customer ID. So based on this, and we want to compare these three together. Now, which test condition is the best looking at this? And I'm going to provide a brief explanation of like these tests. So for example, when you test on gender, if gender, let's say, sorry, if it is yes and no, this should be, for example, male and female, okay? So for example, if gender is male, then 6 cases belong to class 0, and then 4 cases belong to class 1, right? And then also for females, 4 belong to class 0, and 6 female belong to class 1. So this is what it means here. Again, for car type, if you split on car type, what are the distinct values of car type? It's family, sport, and luxury. So the branches, possible outcome or branches are family, sport, and luxury, right? Now, if car type is family, so for car type family, which is here and here, right? What is the class label? Here is 0, here is 1. So 1 case belongs to class 0, 3 cases belong to class 1. You do similarly for a sports luxury, right? Now look at customer ID. what are the distinct values of customer ID? As many like values that we have like in our rows, right? So we have 20 distinct values, which means customer 1, 2, up to 20, right? So these are 20 distinct branches. Now, for example, for customer ID 1, right, belong to class 0. So there is only one case because there is only one here, right? So all cases here, which is only 1, belongs to class label 0. And the same thing continues until the last customer ID. So can you tell me which test condition is the best?
Would it be car type?
Yes. Can you explain why? That is actually the best test condition.
Oh, so like for car type, it seems like it produces the much purer nodes, especially for like sports, where it's like 8 for C0 and 0 for C1, and also luxury.
Yes, that is true, but I'm going to ask another question, and anyone can answer this. What is the purest? Don't think about which test condition is the best, but which of these three resulted in the purest outcome?
Customer ID.
Customer ID, right? Customer ID. Now, why didn't you tell customer ID is the best split? Is the best attribute to choose for the split?
Because the entropy would be 0 with that.
Oh, okay, entropy 0 means information gain is higher. Means the perfect. It's perfect. This is what we want. If entropy is 0, means it's the purest, and that's what we want. But why in this specific? So for example, if here, let's say for gender, if out of 10 cases here, for example, you had let's say 0 here and 10 here, right? Something like that. And then here like this, so this would be the purest and is actually really good. But why here will be overfitting? Exactly. So this is great answer, overfitting. We choose customer ID because then is we have too many distinct values, right? This is like the split is meaningless. It doesn't generalize. And so car type is a better split because branches are purer in general, and most cases belong to the same class. So as you see here, for example, here out of 4, 3 of them belong to class 1. Here this is completely pure because all cases belong to class 0. And again here most cases belong to class 1, which is again like highly pure. So the best one in this like among these three, between these three, is car type. And so this is actually limitation of this method because I'm going to explain about this limitation later. So how to determine the best split? So decision tree, as I said, use a greedy approach. So at node, we make a local decision. We choose the split that look best right now. And nodes with purer class distribution, we prefer the nodes that have purer class distribution. And so how do we measure that? We have to measure impurity, for which we use entropy, right? And so here in the first node, we have 5 examples of each class, which means highly impure, right? And then in the second node, we have 9 from, for example, class 0 and 1 from class 1, which means it's much purer. So this case is highly pure or low degree of impurity, right? So that's why I measures like entropy capture this difference, right? They assign a higher value to mixed nodes and lower values to pure nodes. So the purest node would end up with entropy 0. And so our goal is actually to reduce impurity as much as possible. So this is the last question, and then I'm going to explain information gain like this formula, which is based on entropy, and that's why I explain entropy first, because you need this to calculate information gain. I'm going to explain this in the next session. This is a measure we use to choose the best attribute. So based on like this formula, whichever, so you have to actually calculate this formula for each attribute. So these are your attributes. For example, you have to find the gain of gain is information gain, same as information gain, okay? So they're the same thing. So you have to find the gain of your set or your data based on, for example, attribute, let's say overlook, okay? And then the same thing for example, temperature. And the same thing for all other attributes that you have. How can you make this? You have to first find the entropy of your whole set and also entropy of all like these subsets. So this is, I'm going to provide more examples and explanations, next session, but like as a wrap up for this session, let's do quickly the last iClicker question for today's session. So it asks which node has the lowest entropy. So the higher the entropy, it means the higher the impurity, right? So when the entropy is lower, it means it is purer. And when it is purer, it means it mostly belongs to the same class. Okay, so let's see the responses. Okay, the responses are mixed. Most of you selected option A, which is the correct answer. This is the purest, right? Here entropy is 0 because all examples belong to one class, belong to class yes, right? It's positive, 10 positive. So this is the purest. And then can you tell me which option has entropy equal to 1, which is the highest impurity? Option C, exactly, because half cases belong to one class, half belong to the other class, and this was the highest impurity. So that's it for today. Do you have any questions?
Hello?
Hello. Yep, I'm listening.
Hi. I have one question. In an example that you did some slides back with the outlook and the sunny temperature stuff table.
Here?
Yeah. Just,
sorry, the example with the outlook and temperature.
Yeah, with the tree.
Okay, here.
Yeah, how come overcast it never like continue, it never split?
So as I mentioned, looking at your data, which days the outlook is overcast? So
D3,
outlook overcast
D7
is D3, right? D7,
yeah.
D12, and then D13, right? What are the class labels there? This one is yes, and then this one is yes, right? This one is yes, and also this one is yes. So they all belong to the same class label. And I said when all examples belong to the same class label, we reach to the leaf node and we have to stop. Why? Because there is no point of splitting further, right? The whole point is to make a prediction, and these are our predictions, right? This is a class label column. So at the end, we want to use it for a prediction. So for example, let's say I give you a new case, day 15, right? So based on this historical weather data, I give you a new case and I want you to predict whether the weather is okay for playing tennis or not, right? Now, let's say outlook is overcast, right? Let's say outlook is overcast. Temperature is hot. Humidity is, for example, normal. Wind is weak. So what is your prediction? So you start from the root, right? And so you check the overcast, right? So when the outlook is overcast, as you see, always in the past, whenever the outlook was overcast, the playing tennis label was yes. So our prediction would be yes, we don't need to split further, right? Whereas if we have mixed classes, like for example, look at the sunny case. Look at the sunny case here. For example, here, these are no. But here, when outlook is sunny, one of them is no, the other is yes, right? Or for example, here, sunny, it is again yes. So out of 5 days when the outlook is sunny, in 3 of days, right, we said, okay, don't go. So this is a negative. Don't go to play tennis. And 2 of them were actually positive, that is, go to play tennis, right? But we want to see which factor can help us to understand whether, if the outlook is sunny, whether we should play or not, right? So we already know this, that 2 positive and 3 negative, but based on which attribute, right? And that's why we have to further split when outlook is sunny. That's why we have to further split when outlook, for example, is rainy, but not on overcast, because on overcast, all examples belong to class yes. And the prediction is clear. Is this clear?
Yeah, thank you. Thank
Okay,
you. That
no
makes
problem.
sense.
So do you have more questions? Okay, so if there are no more questions, I end the class. So I stop sharing and I end the recording. I also hold regular office hours every Wednesday. So just wanted to remind you that there is an office hour every Wednesday. So I'm also going to stop recording. Have a great evening, everyone.
Professor.
Thank you. Have a good day. Have a good evening.